Hi there. Today we are going to keep on working with our rational equations, not solving quite yet. Today we are going to continue finding the lowest common denominator, the LCD, and then we're also going to be looking at finding extraneous solutions and domain restrictions. So let's get to it. We've seen the word extraneous solutions before, and in this case there's going to be two kind of things that we're looking for. First, an extraneous solution does have something to do when there is an undefined fraction. Fractions are undefined, you can't do them when the denominator is 0. We've talked about that before, so remember that it's okay if 0's on top, that's fine. That's okay if 0's on top. K can just be some number, but you cannot do this. No to the 0 being at the bottom, right? So this is the situation that we're looking at, the no one, right? So that's what's going to create some undefined fractions when we have that denominator as 0. All right, so then another way that we've seen extraneous is when we plug an answer that we get after solving into the equation, it ends up being false. Like it doesn't make a true equation. It's not equal on both sides. All right, so let's check this out. First, just straight up extraneous. We're not talking about how to solve yet, so let's just say Ms. Gamboa solved this equation. We'll learn how later. And let's just suppose I got these two solutions, x equals 3 and x equals 2 as possibilities. They could both be solutions, they could both be extraneous, or maybe only one of them is. So is one of them extraneous? So here's how to test. Now, you don't always know which one to try first, but I'm going to show you which one ends up being extraneous. Say I was going to take x equals 3 first and plug it in. So then I would take anywhere where I see an x, I'm going to replace it with that 3. The rest of the equation is the same. 4x means we're going to be multiplying by that value. So x is 3, 4 times 3. And the denominator is x minus 3, so 3 and then minus 3. Now if you calculate this, you have in the denominator 3 minus 3 on both sides, actually. Doesn't have to be on both sides, but if at least one of these fractions is undefined, you're going to get a 0 at the bottom. Then that means x equals 3 is this extraneous solution. It's also a domain restriction because we're restricted. We can't have 0 in the denominator. So the solution that is extraneous is x equals 3. And that's extraneous, so it would be like one of those false solutions. I wouldn't even actually box it just because we don't want to say that it looks like a good solution. So x equals 3 is extraneous, it would make the equation false. So they don't always have a solution. Sometimes when you solve rationals, there's no solution. In this case, there is going to be a true one, and to be able to tell, I'm going to show you with x equals 2, because this one is going to work out. So then if we take the original problem, 8 over x minus 3, and replace the x with 2, we're going to have this. Same kind of setup, everything's set up the same, but now we're just going to put a 2 in place of the x. And then from here, we can calculate and simplify it. So it's 8 over, and then 2 minus 3 is negative 1. And then on the other side, 4 times 2 is 8. The denominator 2 minus 3 is negative 1. So you get 8 over negative 1 equal to 8 over negative 1, which is obviously the same thing. So that means that we have a true equation, and like it's true, equal on both sides. And so x equals 2 is a good solution. It makes the equation actually equal. All right, and so that's how you can test them out. Now if you were to plug in a number here, and you would get maybe 8 over negative 1 equals 3 over negative 1 or something. Then that's obviously false, and then you know you have extraneous. All right, so that's how to test answers. We've seen this kind of stuff before, just maybe not in fraction form, since now we're working with rationals. All right, the next little part that we're going to be looking at is going to go back to what we've already done, where we have an LCD. We're looking for the lowest common denominator, but we're also going to show these domain restrictions. These domain restrictions could end up as extraneous solutions. So you find, well, when is the denominator going to be 0? Because we don't want that. X cannot equal that. And then later on when we start solving, it could pop up as an extraneous solution, and you'll know it's extraneous because it'll have been restricted from the domain. All right, so let's get into this one. LCD, a little recap on how these work. Remember, for a lowest common denominator, we are looking at only the denominators. So then, if you need to, you can list out, like everything that you have, the multiples of these. So that x is kind of like a freebie. It's just like a 1x, and 1s are always freebies. But there's definitely an x involved, so the LCD is going to have an x in there. Then the rest of the numbers, and if you want to list it out, let me go back. You can do 1x, 2x, 3x, 4x, 5x, 6x, so on. Running out of room. All right, so you can do that kind of thing with the ones. Now the 4, you're going to count by 4s. 4, 8, 12, 16, and so on. And then 6, 12, 18, 24, and so on. All right, so I've just listed out each of these and did the multiples of them. So the lowest common denominator is the lowest number that they all reach. And I didn't list out the ones far enough, but you can kind of think about it. I mean, 1, 2, 3, 4, 5, it's going to hit all the numbers. So there's going to be somewhere in this list, there's going to be a 12x in there. And you can already see how there's a 12 here, there's a 12 here, and then there's going to be a 12x if I continue the ones. So the lowest common denominator is going to be a 12x. Counting by 4s, 6s, and 1s, they'll all hit 12. X is involved. All right, so that's what we were doing the other day, the previous lesson. Now the domain restrictions go back to up here, what I had mentioned, how you don't want 0 in a denominator. That's going to be restricted if a number makes 0 happen. So when we're looking at these are kind of simple looking because 4 is always 4, 6 is always 6. X is the only one where there's a variable happening. So this is the only one I care about looking at. And so here, there's nothing going on in the denominator except the x. So x itself can't be 0. So x cannot equal 0 over here. All right, because then you're going to get 1 over 0, which we can't have. All right, that's what would happen if you plug it in to that first fraction. All right, so that's undefined, 1 over 0, therefore x cannot equal 0. All right, moving on. The next one, we've seen these before with some whole numbers. Consider that this 4 is really like 4 over 1, because 4 divided by 1 is still 4. And then we've got the other denominators are those expressions, the x minus 3's. Remember that those are grouped together. You can't separate the x from the 3. So therefore the LCD, 1's a freebie, is that whole expression x minus 3. You can keep it in parentheses or not. It doesn't really matter. It might help for when we start to solve to think about them in parentheses. All right, so for this domain restrictions here, x can be 0. 0 is not a problem itself. We still don't want the denominator to be 0. So if my denominators are x minus 3's, then that's the one that I need to be looking at. Then I need to make sure that x minus 3 does not end up being 0. Well, then you just solve that equation, add the 3 over, so x can't be positive 3. If you think about it, well, that would make sense, because if you take a positive 3 and plug it in, you're going to get 3 minus 3. Well, there's 0 at the bottom, which is undefined. Right? So that's the domain restriction. This last example right here, similar kind of idea, just wanted to show you another one. Remember, 7x is not a fraction, so technically it's divided by 1, and my denominators are only the 3x, the 1 is a freebie, and the 9. So again, if you think about counting by 3x, 6x, 9x, 12x, 15x, 1s are going to hit everything, and then counting by 9s, 9, 18, 27. Well, 3 goes into 9, 9 itself hits 9, so the LCD is 9. Oops, let me use pen. 9, and the x's are involved. All right, so then finally, x cannot equal, well, there's only one area here where I have a variable in the denominator. 7x, yeah, there's a variable there, but it's on top, so that's not going to be a restriction. This is the one to worry about. So we just need to figure out when that 3x, that denominator, should not come out to be 0. Well, we'd have to divide the 3 to isolate x, so we end up with x not equal to 0 divided by 3. That's not undefined. That's like this situation up here. It's okay to have a number at the bottom, 0 on top. So 0 divided by anything is still just 0. So here, again, x cannot be 0 itself. It's not always a 0. It can be a number like this. It kind of depends on what your denominators look like. All right, and so that is LCDs as well as extraneous solutions and domain restrictions.